So, greetings. In this video we will continue with this topic of time model scheduling, and I will prove that the interval between algorithm is too competitive. Remember, it was this guy. So it just waits till all the machines are idle, and then it will just schedule at that time point all the jobs which are available in an optimal way. Now I will just prove that the INTV algorithm is too competitive. Okay, the INTV algorithm is too competitive, so let's just consider scheduling produced by the INTV algorithm. The scheduling produced by the INTV algorithm. So it's just, as I've said before, I have a number of machines, and the INTV algorithm can be seen as something which just produces phases of these, say, stair-like sub-schedules, because we can assume that the INTV algorithm will use the first machine to have the largest load in the phase, and the second one to have the second largest, and so on. So, for example, this is a possible schedule produced by the INTV algorithm. I will draw one more, like this. Shouldn't do what things. Good. Okay, now in this figure, in this scheduling, I will denote the time required for scheduling the last amount of jobs by t3. So this is just the length of this interval, the make span of the last part, and this will be t2, the the penultimate phase make span, and t1 will be all the others. So t1 is a time point when the one before the last phase starts. Now, a thing which you should realize that all these jobs, so these jobs which get scheduled here, are not available at this time point, because otherwise they would get scheduled, in the previous phase. So this means that all these jobs all arrive after t1. Yeah, that's great. And this means that the optimal cost, so the optimal cost is at least t1 plus t3, because these jobs arrive after t1, and t3 is an optimal schedule just to schedule these guys. So this means that if I only have to schedule these jobs and just forget all the other jobs, then even in that case I will end no sooner than t1 plus t3, because t1 is a timestamp which is which cannot be larger than the arrival timestamp of any of these jobs. So even if all of these jobs arrive at t1, the make span will be at least t1 plus t3. Now, and also to schedule only these jobs for these, even if they arrive right at time point 0, why not? So for these jobs only, we again have this optimum is at least T2. And well, this means that if I just sum these two, let's think that twice the optimum is smaller or is larger than T1 plus T2 plus T3, which I could write as 2 times L star, so the optimum is at least L, because this here is just the make span of the INTV algorithm, and this means that L divided by R star is at most 2. So this is easy. The INTV algorithm is too competitive. That's great. But there is a problem with the INTV algorithm. Namely, how should we produce always the optimal schedules for these parts? Now, producing an optimal assignment is a very hard problem, so it takes exponential time according to our current knowledge just to produce these guys. So INTV has variance. INTV has variance. So for example, the INTV plus LPT algorithm is almost the same as INTV, but instead of scheduling optimally in each phase, it just schedules according to the offline LPT algorithm. According to the so-called offline LPT algorithm. So the offline LPT algorithm says that just sort the jobs, the available jobs, of course, because the INTV algorithm just waits, and if everything is idle, each machine is idle, and we have a number of jobs, then we can make, say, an offline optimization on those jobs which are already available. So sort the jobs in decreasing order with respect to their processing cost. What's the cost? And then schedule them using list. Using the list algorithm. Now, our previous example is not that educational for learning about this algorithm, and I will just have to look up for another input, because it turns out that our previous example is just producing the very same output as the optimal one, but I'm just trying to fetch one good input for the INTV+LPT algorithm. Okay, so for an example, I'm not sure whether it will be more education than the previous one or not, but I will talk about what happens. So m is 3 and we have an input of 1 0 2 0 3 0 2 1 2 1 3 2 4 3 5 4 and 2 6, and we just have to run the INTV+LPT algorithm on this particular input. Now, okay, so where should we proceed? First, I'm just switching colors, right? So I have 3 machines, right? Then at time point 0, I already have 3 available jobs, okay? Since I'm running the one variant of the INTV algorithm, I'll have to schedule all of them, no matter how many machines I have and no matter whether they will fit on single machine. And since I'm optimizing these jobs, which are already available according to the LPT algorithm, it means that I have to sort them in a decreasing order, so it will be 3, 2, and 1 with all the timestamps, and I'm just scheduling them according to the list algorithm, which means that in the first machine we'll get the first job, the second machine has the smallest load at this point, so it will take the job of size 2, and then the third machine will have the smallest load, so it will get the job of size 1. Okay, so that's good. And then it will wait till time point 3, time point 3, time point 3, time point 3. That's it. So I have 4 jobs available, and again I have to schedule them. Okay, so I can just write the timestamps out, okay, explicitly. So I'm just sorting these, so it's 4 3, sorting these which are already available, 3 2 2 1 and 2 1, okay, and I'm just scheduling these guys according to the list algorithm from this time point on. So the 4 3 will be put here, and then the 3 2, since this guy is the least loaded machine, and amongst the 2 least loaded machines this has this smaller index, it will get put there, and then the 2 1, yeah, that's great, and then the other 2 1 will be put here, because at this point this machine has the smallest load. Yeah, okay, so all of these machines are running again till all of them become empty, and then finally I will have this 5 4 and 2 6, and then the total make span will be 3 plus 4 plus 5, which is just 12. It's probably not optimal, but it doesn't really matter at this point of time, so I'm just showing you an example for INTV+LPT. So once again, INTV means that we will wait till all the machines are idle, and then we will schedule all the jobs which arrived during this waiting period, and then the scheduling itself of these jobs which arrived is done according to the LPT algorithm, which is an offline algorithm. So we just sort the jobs which have to be scheduled right now in decreasing order according to their processing times, and then we use the list algorithms, the original list algorithm to actually compute the scheduling. So the INTV+LPT algorithm versus the original INTV. So the pro is that it's faster. So it's faster to compute, because in the INTV, so the INTV algorithm, we have to compute an optimal scheduling, which if you have, say, 1000 jobs on, say, 10 machines, it will be like impossible to create the optimal solution. Now, of course, everything has a price, so it's only 8/3 competitive. So INTV was too competitive, and 2 is a smaller value because 2 is 6/3. So the INTV is better in terms of competitive ratio than the INTV. Now the INTV plus LPT algorithm is 8/3 competitive, basically because the LPT algorithm is not producing an optimal solution, but its so-called LPT is a 4/3 approximation algorithm. Now this means that it's very similar. For an offline algorithm to be an approximating algorithm, it means that it's fast, okay, but it doesn't necessarily produce an optimal solution, but the cost provided by LPT, the cost of the solution provided by LPT is at most 4/3 times the optimal. And in general, if you use an algorithm having an approximation ratio of, say, alpha, then the INTV plus the algorithm which uses that alpha approximating algorithm inside will be a 2-alpha approximation, 2-alpha competitive algorithm. Basically, because if you just look at this previous part, it will mean that okay, so if you just, so all these jobs arrive after T1, and if you just have an alpha approximating algorithm scheduling this part, then of course the optimal value is at least T1 plus, say, 1/alpha times T3, because locally the optimal solution cannot have a smaller cost than this T3, and also for scheduling only these jobs, we also have that the optimum is at most 1/alpha times T2 if the algorithm used inside is an alpha approximation algorithm. And if you just add these two things again, we get that twice the optimal cost is at least as large as T1 plus 1/alpha T2 plus 1/alpha T3, okay, which is, well, since alpha is at least 1, it becomes 1 if we actually compute the optimal solution. So this is just this is just larger than 1 over alpha times t1 plus 1 over alpha times t2 plus 1 over alpha times t3. And if I'm just multiplying this by alpha, I will get the 2 times alpha times, well, instead of opt, I will just write L star is at least as large as t1 plus t2 plus t3, which is of course L. So I again have this L divided by L star is at most 2 times alpha. So this is how it can be shown. But basically, if you have an approximation algorithm inside, say a 4 over 3 approximation algorithm, then the INTV algorithm using this offline approximating algorithm as a subroutine, you will get a 2 alpha competitive algorithm. So that's why the INTV plus LPT algorithm is 8 over 3 competitive, because LPT is 4 over 3 competitive. You can find a proof in the lecture notes of this fact. LPT is a 4 over 3 approximation algorithm, but it's not a part of the curriculum of the online algorithm course. So that's why I'm just stopping here. And this was the last video about some variant of the scheduling problem. Next time we will just move on to the list access problem. Till then, bye bye.